All right, good afternoon, everyone. Welcome to CubeNexus's first webinar. I am Stephen, co-founder and CEO of CubeNexus. We've got some of our other teammates here. My co-founder Adam is on the call as well, our head of engineering Peter, and then our two senior engineers, Adam and Jacob. So they'll be responding to your questions in the chat. Just as a overview, this is webinar style, so question and answer feature should be open. You can ask questions at any time. And as we respond, they will get put into the chat for everyone else to see. If there is a question that is overly complex or requires a deeper explanation by one of my team members, I'll pass the mic over to them. We'll do that after a short presentation and a demo of the platform. We'll probably save about 10 minutes at the end of the call for Q&A, but you can always be asking questions throughout the entire webinar. So the context here is that CubeNexus launched our Decision Intelligence Suite, our AI platform for spatial data, about a week ago. We'd had it in beta for from the beginning of June till last week, getting feedback. And now we wanted to show a real world use case of why the data structuring that CubeNexus has pioneered is critical and value add across industries. Today, we're really going to be focused on an aviation air traffic control explanation and demonstration. And that's surrounding the January 2025 DCA Potomac River crash. So I'm just going to go through a short kind of background on the crash. Shout out to our friends over at Vast Aviation for putting together a little summary of what happened back in January. A little context, what CubeNexus does is takes diverse data sets, diverse types of inputs, everything from aircraft transmissions to geospatial data sets to sensor data sets, radio frequency transmissions. Eventually, we'll be able to do LiDAR, video, camera as well. And we integrate those up into a three-dimensional view of all of the data over time. What we're really talking about here is giving context to the data that you are working with. So in January 2009, we had essentially, just for those who don't know, we had two aircraft traveling down two different corridors around Washington, D.C. One was a Black Hawk helicopter coming from north to south, and one was a American Airlines RJ aircraft. I'm letting the video play just so you can kind of see what an air traffic controller would see. Kind of a critical aspect here is if you look at most data analysis out there, whether it's in the energy sector, whether it's in telecom, whether it's in aviation, primarily all of the interfaces that air traffic controllers, analysts, all the way up to CTOs have to work with is in two dimensions. So this is basically what an air traffic controller sees. Radar pings, transponder pings in two dimensions. No true context to all of the other information, such as the maps that you see below this image. The air traffic controller wasn't able to see this at that time. So one of the takeaways we hope that you'll see is that if data is structured based on how the CubeNexus geospatial framework works, we can paint the full picture for this ATC, this air traffic controller that was looking at this incident, and for anyone else who's analyzing a multivariate, multi-sensor, multi-domain set of data. Here you see the PAT 25, which is the helicopter. I'll be referring to the helicopter as PAT 25 coming down the Potomac River. And I think we all kind of know what happens. I'll skip forward in the video a bit. And you can see, the collision happened just around, 8 p.m., 8:40, 8:43, 8:47 that evening on the 29th of January. You'll see some references in our data sets to the 30th of January because we convert to UTC. But this is what happened, and this is kind of the scenario that we are discussing today. So how does CubeNexus actually get involved? So what we do, as I mentioned, is we structure data. At the end of the day, you're going to see a beautiful platform that our engineers have built. You're going to see an LLM interface. You're going to see some really cool analysis that we can do. But at the end of the day, what undergirds our entire platform is the ability to take disparate types of data, everything from these data sets here, the helicopter flight plan. This is where they were supposed to fly, the American Airlines flight plan, their diverted route to runway 33, which is what actually caused the accident, the actual flight path of the helicopter, real-time data, and the American Airlines flight plan. We put in post-crash data as well, so we were able to ingest air traffic control transcript of the event and the event timeline itself. All this to demonstrate that the true value add of CubeNexus is overlaying these diverse layers of spatial data over time so that we can identify abnormalities, we can identify risk areas more quickly and more efficiently than the status quo. So a little bit of visuals just for context before we get into the platform. Basically, this is the status quo. This is what ATC is working with. This is what airline pilots are working with. They're working with flipbooks, maps, ATC, again, here in the center, seeing a two-dimensional version of where the aircraft are actually flying. What we did is we took these data sets, which we actually are able to convert to a Excel file, a CSV file, and we parse them into our cube-based data format. What we do essentially is we add the three-dimensional and time series nature of the data. You'll see like on all of these data sets, these are Excel CSV sheets of the data that you just saw. This is basically the runway in lat long, the path of the helicopter in lat long, the American airline in lat long. The problem and the reason that this crash was not prevented 10, 15 minutes previously, the reason why the ATC air traffic controller made a mistake and diverted them to a runway that they should not have diverted them to was because of the inability to see this whole picture of all of the data at once. Therefore, it slowed decision making and caused a mistake. So we essentially take these data sets in our platform and we parse them. We are able to assign them a specific cube or specific set of cubes that they sit in. And these are all volumetric. So they are in 3D natively. A lot of air traffic control, air situational awareness, even in other sectors, telecom, coverage maps, if you're doing subsurface mapping for an oil and gas company, primarily you see the data in 2D. We transition it all into a 3D perspective to give true context because, let's face it, we live in a 3D world. We're also able to parse the actual text. So this is kind of standard LLM. AI can already do this. We're able to pull information on location data out of transcripts, out of the event timeline, and add that as additional context for post-crash analysis. So we're basically going to show you both how we can do some pre-crash analysis. We could have prevented this. We could have notified the ATC of the collision zone 4 to 15 minutes earlier, depending on what happened, but definitely sooner than the 45 seconds or so that he had. And we're going to show how we take all of these different types of data and put them into one universal picture, one time 3D space. And that's what allows us to ID collisions 15 minutes prior. And essentially, if our system was implemented in an air traffic control environment, we could essentially build bubbles, cuboid bubbles based on our spatial reference system around every aircraft and prevent a crash like the DCA crash from ever happening. So I'm going to stop presenting right now the deck, and I'm going to hop into the platform to show you how this works. All right, you should be seeing CubeNexus.ai right now. This is part of a kind of journey we've been on from a user interface perspective. How do users really want to interact with their data? And we realized one of the biggest challenges is actually just getting users, getting companies to actually ingest their data. So right now in this version, there will be updates in the future, but we kind of start with allowing users to upload data and to ingest data. So if you go onto the platform right now, if you sign up for an account, you can do this. So I'm just going to show you kind of the process we went through. I click this upload data button, and I'm not sure if you can see the file explorer, but I basically have those data sets that I showed on the PowerPoint right here. I have the text files of the context of the timeline and the runway that the American Airlines aircraft was diverted to, the route that the helicopter was supposed to fly, the route that the helicopter flew, and the flight that the aircraft flew, that the American Airlines flew. So when I select all of these, I'll select the CSVs. You hit open. These are going to upload. I'm not going to go through the whole process just for time, but essentially then you go through just a very simple choose which column was the date and time, choose which column was the lat long. It's usually pretty easy. Like, it actually says lat long. For elevation down here, you choose altitude. And you can do this one by one for each file. So for an individual user, you can go and start ingesting data sets up to thousands of rows of CSVs or Excels and basically standardize the time space format of your data. So I'm going to now go to the next tab to show you kind of what this looks like. So one of the real differentiators of CubeNexus is we do everything in 3D, as I mentioned. So this is a visualization basically of where the runway approach points are for that American Airlines aircraft. You'll see the cubes there, but when I turn the Earth on, you can see that they basically overlay on top of Reagan International Airport right here. So if I kind of toggle on and off the cubes, we're basically saying this is where the runway was. Similarly, if I go to the next tab, we've done the same thing with the American Airlines flight, right? So we've taken that data set, CSV Excel data set of all of the lat longs of where that aircraft flew from Wichita to DC and reconstructed it in a standardized 3D format. So this is essentially the reconstructed flight path of the American Airlines flight. This right here is the reconstructed flight path of the helicopter. So as you can see, I'm trying to demonstrate that all of these data sets are getting unified in time and space into the same 3D visual. And not only is it a visualization, but it's also a AI native, AI interactive. We're basically turning data sets into language for the AI to understand and for a user to interact with. So then the real magic is when you overlay all of these on top of each other. So when you take all of those different data sets and you put them into the same system, now you have the reconstructed flight path of all of the aircraft, where the runway was, where it was supposed to land, and the AI backend now has all of this context of like, okay, basically the routes that they were going on were like railroad tracks, right? So when the air traffic controller diverted the American Airlines flight to a different runway, it should have been immediately obvious to the ATC that there was a collision bubble, that there was basically a space, and we've highlighted this in dark blue right here in the center, that this space was a potential collision zone. Really, this should have been known about 15 minutes earlier, and I'll show you how we get that insight in the LLM. But that should never have happened. The aircraft should have been diverted around as the helicopter passed and then landed on a separate runway. But because this collision zone was not identified immediately, and because it wasn't highlighted to the ATC, it was missed, right? We succumb to human error. All right, so now I am going to kind of show you the way that we can actually interact with this data. So on the platform, how do I interact with this? In future iterations, we're imagining building, an air traffic control agent that is active, notifying the user, or an agent for another geospatial application. But right now, it's pretty user-centric. So we have to ask the questions. We need to derive the insights. So I'm going to basically bring up another list of queries that we have brought up. Now, as you kind of interact with this platform and load various data sets, I encourage everyone here to, go download public data sets or take data sets that have lat long on them that, in your work, and test this out, because it's pretty interesting and pretty revealing once you actually start to engage with it. The one thing I will just show you is on this next screen, the way that we can view a lot of other types of data. So this is like all of the airports of the world, but we'll just focus on the aircraft itself. So if I start to, query here, I'm going to ask some questions. of the data set. So we have everything loaded in here. We have the path, flight path, the aircraft. We have the runway where it's supposed to land. And I'll show you, I'm going to exit out of the visual real quick, and I'm going to upload the timeline and the transcript just so we can let's do some post-crash analysis. Okay. So now I'm going to ask a question. So if you go into the transcript, the crash happened at 8:47 p.m. Eastern time. And I'm going to ask, all right, I'm looking at this, and at 8:33, so earlier, that's when the ATC diverted. That's when the ATC diverted the American Airlines flight from its initial path to runway 33 because there was, the helicopter. He was told that the helicopter was coming. So I'm going to ask at 8:33 p.m., was there a possibility of a midair collision between Route 1 and 4, which is where the helicopter was flying, and runway 33? When you ask these queries, basically the LLM is pulling all of those data sets that we uploaded and using its LLM context as well. So, we're using a llama model. You can see up here, the 70 billion instruction up here. So this is a llama model, a meta model. And you can see that at 2033, there was a possibility of a midair collision between Route 1 and Route 4 and runway 33, and then it goes through the explanation. We've built this to be very glass box. So you can actually, inspect the reasoning behind the answer. I'm going to ask another question because 4 minutes before the crash, there was another possibility of notification. Now, the air traffic controller did not realize really that there could have been a crash until about 90 seconds before, and by then it was too late. So when I say at 4 minutes before, yes, there was a possibility of a crash, and essentially it's explaining that because these aircraft, it knows the velocity of the aircraft, it knows where that collision bubble is, that this is a possibility. I'm just going to ask a simple knowledge question just to show that it can pull knowledge. So I'm going to ask when was the call made by the ATC to clear the landing? And it's going to pull from the transcript actually. And it's going to pull up the visualizer again. I'll close the visualizer just for so you can all see the text more easily. And then I'm going to ask a different question about the collision zone. So based on this, where was the collision zone, the collision cube? We call them tolls, which are time-united locations. Where was this no-go zone? So it's basically saying, where was this interaction happening on these cubes in these two aircraft's flight paths? And it's basically telling me the location, and it's telling me the lat long and the altitude of where exactly that 200 meter cube is. And then the last question I'll ask is, how much in advance could we have known the collision would happen and why? And there are several right answers to this question, so we'll see which one it gives. It could have been 90 seconds, it could have been 4 minutes, it could have been 15 minutes. Oh yeah, and see, it's going to give the 4-minute one. So right here, 4 minutes and 53 seconds in advance. And that's a substantially longer, it's about 4 times as long as the air traffic controller actually had and actually was notified. So I'm going to pause there because I want to give about 10 minutes for questions. I know some questions have been asked in the chat, so I'm gonna stop sharing this and go back to the deck. And bring up the Q&A. So anyone, please, if you have questions, feel free to answer or to ask them in the Q&A box that's at the bottom of the Zoom. We do have, let's see, I am able to allow people to talk. So if you want to ask a question in verbally, feel free to raise your hand. And if you want to ask about other applications, and if you want to, actually ask a question to Adam or to Peter or, any of the rest of our team, we can answer. All right, Jeff, I'm gonna click allow to talk, and then you should be able to unmute your mic. All right, go ahead, Jeff. Can't hear you. Okay, Jeff, sounds good. Jeff's gonna resolve the audio on his end. Jeff, just raise your hand when you want to speak again. All right, we have a few questions coming in. I'll answer. Adam is typing a question, but are the cube sizes standard? So our system is nested and recursive. So let me share my screen again to essentially show you. Think of the CubeNexus cube system as a like MGRS2, if anyone's familiar with like MGRS, which is a grid system that the military uses to cover the Earth. So let me go to here. So what you see here is, see how there's like levels of cubes? The largest cube is 20,000 kilometers, so it surrounds the whole Earth. That's why we can do outer space data coming from low Earth orbit. And then every cube is basically, think like a Russian doll. It's divided by 1,000, 1,000, 1,000, 1,000, 1,000. So what you're seeing here, when I go to the color by ID, right? So that's colored by ID. If I don't color by ID, you see how there's like a huge cube, like a green one that's like 20,000 kilometer cube, and then 2,000, and then the orange one is 200, the purple one is 20, and it's just base 10 all the way down. So we can go all the way down to like centimeter, millimeter, sub-millimeter level. Think of it as like, you're not seeing the data itself on the screen here, you're seeing where the data is spatiotemporally. So it's like, think of it like the HTML of spatial data, to where whenever we query or we visualize or we want to identify something in time space, we know like an address to go to of where that data is.
So one thing I want everybody to understand with the cubes is, for example, in our GPS denied navigation system, that we're able to turn these cubes, which are called tolls, time united locations, into a standard set of relationship between each and every other cube. So because we have the nested recursive structure, every time that you go down to a child level, there's another 1,000 cubes and another 1,000 cubes, another 1,000 cubes. This immutability allows for us to use a very, very simple equation, which is distance equals rate times time. That's how when we're doing our navigation and we're able to see timing, we're able to predict when things are going to collide, just like if one train leaves a station going 30 miles an hour, an hour later, another train leaves the station going 60 miles an hour. They meet at the 2 hour mark. Something so simple as that is now able to be done because we don't use the center of the Earth as our reference point. We convert all the lat long and all the air of the lat long, like the shaded area on a GPS, into our cube system, which is called tolls. So when you have a toll, you can have a reference from any other toll in the system, not only in not only in spatial geospatial movement, but also over time. For example, something that's in 1920 can now have an R squared relationship to something that is today in a completely different location. This is the real power of the system. And if you're familiar with how eigenvectors work and all those other things, we can definitely take that offline and show you how we can do some very, very powerful math with this.
I'll just show you just Adam's point about time. So, one of the things that's very critical when you're synchronizing different types of data is the time, right? So it's a huge challenge in navigation. It's a huge challenge in IoT, SCADA, synchronization of those data sets. So we synchronize all of time within the system. Like that's one of the first steps when you upload data, or when we pull data from the cloud of another customer of ours, and we parse it. We're synchronizing the time, and we're synchronizing the 3D location. So you see the slider bar down here. So this slider bar is essentially like demonstrating the time series nature of this data. So, you have, July 17th. This is like a day scale. So the scale would need to be brought down to like within 6 hours. But essentially, if you, slider bar it over, obviously, as soon as I like leave January 29th, everything disappears because all the data is on January 29th. All right, Jeff said the question that he had was the same as Kevin's. Chris Stark asked, are you implementing this application with any aircraft systems in a GPS denied scenario? Not right now. Adam, do you want to give a kind of update on where we are with the GPS denied navigation piece? Because the SaaS platform, Chris,
what we're doing right now, what we're doing with GPS denied, we've already demonstrated that we can do GPS denied with any signal of opportunity. For example, we've taken SDRs and encoded the FM band characteristics of the actual frequency, so 88.0, 88.1. And because we're putting those values into that toll, and now that toll has time and united with location, and in our terms, 9 dimensions of understanding, we're now able to understand where everything else is just from that one toll, and then another toll, and it starts to feed the information. We don't navigate off picture matching. We don't navigate off of like a VOR tower or any other kind of station where I have to do a TDOA or time distance of arrival. We do it specifically from the value of this data set to the value of that data set. What would have to be the value of the data set that I'm in that is currently unknown? And so what we've done is we've turned our tolls that you saw there, all those cubes, we turn that back into a NEMA stream and put that back into the platform. So your RG pilots, your PX4s, Cube pilots, we're actually going directly into the GPS port. So the RG pilot system doesn't know that it's not getting GPS. It thinks it's getting GPS. It's just from a very robust system from the CubeNexus system, instead of just one phenomenology, which is GPS timing. Does that answer your question?
Chris, we'd love a letter of support for you on one of these SIBRs, man. Like that would be sweet. Because we're proposing to one right now for our GPS denied solution. This SaaS product is like in market right now, so I'll just kind of finish with that. You guys can try this out. I would share it ideally if we had to have people to try and start uploading data. We're talking like data analysts, GIS people who are working with time-space data to go try this out. We're also aware of numerous other companies that are building mapping softwares, air traffic control softwares, mapping softwares. All that is in 2D. Come talk to us. We'd love to turn your 2D into 3D. Because if you structure the data with us, that is like an inherent benefit you automatically get. So I know we're at 2:29. I would love to have anyone who was interested in a follow-up call email me. My email's there. I know I've talked to some of you before, some of you I haven't. Appreciate everyone who I've never met who's on this call. Really awesome of you to show up. We will hang this webinar after the downloading, and it's all finished. We'll put it up on the website, so we'll share it with people who couldn't be here. But I do want to thank you everyone for taking your time to be with us today. Thank you to our team at CubeNexus for all the hard work you've done over the last 3 months to get this to where it is. It's amazing. And we're only going to keep building awesome features, but we need feedback, and we need to know what the aerospace, what the aviation space, what the ATC, what the energy space wants and needs. So feel free to reach out. I'll let everyone go now. And thank you so much. Have a great rest of your week and a great rest of your Tuesday. So have a good one, guys.